Good day everyone. In this video, we are going to talk about blackbody radiation and Planck's constant. This is Leo Sinelio from BSc Science 3A. Alright, so blackbody radiation that is refers to the spectrum of light emitted by any heated object, and it is an idealized physical body. All incident electromagnetic radiation regardless of frequency or angle of incidence. And Planck's constant, also it is a constant that gives the unverifying ratio of the energy of a quantum of radiation to its frequency, and that has an exact value of 6.626 times 10 raised to the power of negative 34 joules per second, and it has a symbol of a small letter h. Alright, so we have here the equation. E is equal to hv, or that is hc divided by lambda, where the E is equal to the energy and the Planck's constant letter h, and V is the frequency, V, or it could be small letter f, and this is the speed of light in the lambda that is equivalent or is equal to wavelength. Alright, so we have also here the Wien's law. Wien's law, that is the wavelength, the maximum wavelength is equal to B divided by the temperature or letter T. And again, so the E is equal to HV or HC divided by lambda, that is also an object that could absorb all radiation that falls on it. Also, that is the blackbody radiation in the equation, and it is the radiation that such an idealized object would emit when it is hot. And the Wien's law also, it is a relationship between the wavelength of light that corresponds to the highest intensity and absolute temperature of object that emits radiation. Alright, so we have here our first problem. We're going to answer this one. Alright, so we have here an star whose peak intensity occurs that at a wavelength of 500 nanometer. So we're going to find the temperature for this particular star. So on this problem, use the Wien's law equation. So we have here the maximum wave is equal to B divided by T. As we all know that the B is a given, that is 2.9 times 10 raised to the power of negative 3, and the wavelength of 500 nanometer, that is equal to 5.10 raised to the power of negative 7 meters. And what we are going to find, or our task here, is to find the temperature of that particular star. Alright, so here we have our Wien's law equation. Alright, so that is also equal to the in order to find the temperature, so we are going to derive our own formula. So let's divide both sides by lambda. Right, so cancelled out in order to the temperature. Alright, so we have here our final equation in order to find the temperature of that particular star. So we have here our solution. So let's use this temperature is equal to B divided by the wavelength. Alright, so let's all substitute all the given value. We have here the B is equal to 2.9 times 10 raised to the power of negative 3 meter times Kelvin. So that is unit of B, and divided by the lambda or our wavelength, that is equal to 5.5 times 10 raised to the power of negative 7 meters. So that is already converted into meters, since to cancel out all the same units, that is meter. Alright, so we have here 2.9 times 10 raised to the power of negative 3 divided by 5 times 10 raised to the power of negative 7, and that is equal to 5,800 Kelvin, and that is the temperature of. And now let's proceed to our second problem. We have here, it states that what is the energy in joules of the violet light having the wavelength of 395 nanometer. Alright, so what we are going to do is we are going to use the Blackbody radiation equation. So that is E is equal to HV, or E is equal to HC divided by the wavelength. Alright, so as we can see here, we have the given of the wavelength of 395 nanometer, or that is equal to 3.95 times 10 raised to the power of negative 7 meters. So it is already converted. In our Planck's constant, that is letter H, so 6.626 times 10 raised to the power of negative 34 joules per second. And we have also here our speed of light, that is letter C, or that is equal to 3.0 times 10 raised to the power of negative 8 meter per second. Okay. So our equation here, we're going to use the energy is equal to Hc divided by lambda, or wavelength. So substitute all the given values. We have our solutions here. The H here is equal to 6.626 times 10 raised to the power of negative 34 joules per second. And our C, or the speed of light, that is equal to 3.0 times 10 raised to the power of positive 8 meter per second. Our lambda here, or the wavelength, that is given by 3.95 times 10 raised to the power of negative 7 meters. So this is 7. So now let's cancel same units. We have here seconds and seconds, and meters and meters. So that's it. We have already joules remain. Alright, so we have here 6.626 times 10 raised to the power of negative 34 joules times 3.0 times 10 raised to the power of positive 8 divided by of 8, so that is equal to 1.99 times 10 raised to the power of negative 25 joules. And copy our lambda, 3.95 times 10 raised to the power of negative 7 here. So there is no unit because it is already cancelled out. And 1.9 times 10 raised to the power of negative 25 joules divided by 3.95 times 10 raised to the power of negative 7, and that is equal to 5.04 times 10 raised to the power of negative 19 joules. So that is the energy in joules of the violet light having wavelength of 395 nanometer. So that's it for Blackbody radiation and Planck's constant. Thank you for watching, everyone.